Hello, my name is Jerry Kossoff. Welcome to Fiveable. We're going to do some AP statistics today. Going to discuss bivariate data. That's two quantitative variables specifically. We're going to look at advanced linear regression and how to read some computer outputs. Be sure to follow us on all of our channels so you can get all the updates of content that you're looking for. This is part 3 of a 3-part series about scatter plots and regression. I'll review some of the key facts. So this actually can be a standalone lesson, especially if you're reviewing for a unit test, where I'll go through some of the key content. We'll look specifically at how to measure how well the line fits the data if we're looking at linear regression. And there's 2 key measures. You can see them along the bottom. There's that little S in the bottom left corner. That's standard deviation of residuals. We'll talk about what that means, as well as this thing called R squared, aka the coefficient of determination. Okay, and then we'll learn how to read that thing along the bottom. There's a lot of information in there. And so we'll pick out the different components of it, write some equations from it, and then do a couple of cumulative practice problems at the end that can help you ace your unit exam or study for that AP test coming up in May. Okay, so to review from the first couple of lessons, even if you haven't watched them, the first one we learned how to describe scatter plots. And remember that when we're describing scatter plots, when you're trying to answer an AP question like, for example, describe the association shown here between height and arm span, we need to name a direction that's both positive or negative. We need to name the form of the association, whether the dots line up in a way that looks linear or nonlinear. And finally, we need to mention the strength of the association, whether that strength is strong, moderate, or weak. Okay, and the strength comes down to whatever form your model looks like, whether you think it looks like a line or it looks like a curve, how close to the dots adhere to that pattern. Okay, how big would the residuals be if I were able to draw that pattern through it? And so in this case, looking at this scatter plot, I would say that this is a positive, linear, and either moderately strong or just strong association between height and arm span for the students in the sample. Okay, in part 2 of this, we looked at the same scatter plot, but now with a regression line attached. Okay, and that form of the regression line is y hat equals a plus bx. Remember that the little hat on top of y stands for that it is a prediction based on current data that we have, based on the current scatter plot. Okay, and x stands for the explanatory variable. Remember, explanatory goes on the x-axis, in this case, height. Y hat stands for the predicted value of the response variable based on using the equation of the line or using the line that is on the graph. If you had just a regular y without the hat, it would represent an actual output for an individual, so a specific y coordinate that is plotted on the scatter plot. The first variable there, the a, that's called the intercept or constant. That's going to be your y-intercept. So just like in algebra, y-intercepts are the value of y when x is 0. And so that's the predicted value of the response variable when the explanatory variable has a value of 0. And the b is the slope, which represents the average predicted change in the response variable per 1 unit increase in the explanatory variable. We do a pretty deep dive into those two, intercept and slope, in part 2 of this. So if you're looking for a little bit more review of that, you'll definitely want to check that out after this video. The other thing we did in part 2 is defined residuals. Remember that predictions, when we make them, aren't always perfect. You can see the dots aren't all on the line. And so residuals measure the actual difference, that vertical distance between the dots and the line. And the formula for a residual is the actual values of y minus y hat. And if you get a negative residual, like the circled dot would have a negative residual, it's below the line, that means the line was an overestimate. So if I actually use the regression line to predict the long jump for that particular person who sprints that fast, I would have overestimated how far they actually went because they actually went less than predicted. And the same is true with positive residuals, or the opposite is true with positive residuals. I underestimate how far or how big or how long or how much money or whatever we're measuring for the response variable. You end up underestimating it because the dot would be above the line, so the line is too low. And if you're on the line, your residual is 0. Okay, so an example to kind of show some of these concepts in context. Here's a scenario that's shown up on AP exams before. So we got a scatter plot showing that the manager of a grocery store measured the wait time to check out in seconds for 11 randomly selected customers throughout a given day. And the scatter plot and the least squared regression line that relates the number of people who were in line in front of the customer when the customer gets to the checkout and how long it took the customer to check out, the wait time, shown here. So in this context, you look at the x-axis, you see customers in line. That's the explanatory variable. And we're trying to predict how long it will take to check out if you see how many customers are in front of you. And so one thing we could be asked to do is interpret the meaning of the slope and intercept of the least squared regression line. And another thing we might be asked to do is to justify if any of the customers appear to be outliers in the situation. Do there appear to be any outliers in this situation? I want to justify our response. And so at this point, I'm about to show sample solutions to this. So if you're watching on replay, you might want to hit pause right now and attempt to do these two. And then in about 10 seconds, go ahead and turn it back on. And so I'm going to pause for about 10 seconds to give you a chance to hit pause. And then I'm going to show the answers to both part A and part B. All right, coming back with part A in just a moment here. Interpreting the meaning of the slope and regression, slope and intercept. So the slope is what happens when the number of customers increases by 1 at a time. We are predicting that the wait time will increase by 174.4 seconds. That number attached to X is the slope. I highlighted the word predicted in bold so that you understand that you have to say it when you're looking at rubrics. Predicted is a part, or average or expected, something like that is a part of it, as well as intercept. You'll see the word predicted bolded again. And that is when there are 0 customers ahead of you in line, the wait time is predicted to be 72.95 seconds. And if you're watching on replay, use the timestamps at the bottom because I'm going to pause for a moment. If you are just joining us live here, okay, if you could put in the chat what you currently know about scatter plots and regression, if this is totally brand new as a concept, or if you already know some stuff, just so I can get a sense of where you are live. And so I can make sure I tailor this to you. And now on replay, I'm about to go back and discuss part B about the outliers. So in this situation, do any of the customers appear to be outliers? Well, I think there's one down there. When you're justifying your response, it's got to look something like this. So a customer who had 3 people in line ahead of him or her, but took a very short time compared to what was predicted by the least squared regression line, or this customer had a very large negative residual compared to other customers. So one of the things that we really need to make sure if we're describing outliers, okay, know about scatter plots reasonably well, so you're reviewing for test. Okay, one of the things you're describing with outliers is making sure that you compare that individual to the rest of the data. So say like, wow, that dot is really far away from the other dots, or that predicted time is really far away from the actual time based on the other data. And so Lauren, who's just joining us, good to see you. At this point, I'm about to go into interpreting S, interpreting R squared, and reading some of those computer outputs. Is there anything else that you'd want me to review at this point using a calculator to find R squared or S? Okay, cool. So do you know where to put data in on your TI-84? Or do you have a TI-84, or what kind of calculator are you using? Okay, perfect. So you have a TI-84. Okay, you'll want to make sure, and I just realized that I am working this on my new for this year school computer, which does not have my emulator put in it. So I'm not gonna be able to pull up a screen, but I'll try to describe it as best as I can. So you know where to put the data in, and you know to run, so it's not one variable stat. So you'll go to, I think it's choice 4, when you go to the stat calc menu. You scroll down, it should say like A plus BX or AX plus B or something like that. And if you've turned on, what is it called? Oh, there's some feature you have to enable first, because it will show you R squared as a part of that printout, in addition to, I think, R actually, when it shows you the slope and intercept. I'm actually not sure if it shows you S, to be perfectly honest. So I realize it might not be the most helpful thing in the world. But I know that when you put the data in, put the list in L1, put the list in L2, stat, calc, do the one that says lin reg or linear regression with the AX plus B, and it should give you your value of your slope, your value of your intercept, and it should give you some stuff underneath that as well. And what is it called? R squared and R, but not S. Okay, cool. So I'm realizing, S, how would I do that on a calculator? What we'd probably have to do is, which could be really hard, we might have to actually calculate residuals for each point. And I don't know if that's feasible. I don't know if there's a command, because I'll be totally honest, in my classroom, I know that the AP exam doesn't, on the exam itself, doesn't make you put all the list of data in to like print this out. It just gives us the printout and makes us interpret it. So I focus much more on the interpretation. So if you know you can show R squared, that should be good. I would have to defer to your own teacher about like getting S to print out, but I got you on interpreting S coming up in just a couple of minutes here. And so I'll start with, when we're talking about how the line fits the data. Okay, cool. The teacher will give you the S values. Good. Yeah, I'm realizing I'm not 100% sure. That's actually something I should look up a little bit later. So least squares regression. This equation here is the least squared regression line for this particular set of data. And I know that, you know, in Algebra 1, a lot of people call this line of best fit. And they're like, oh, why am I calling it least squared regression line? And it has to do with making sure that something is minimized. That least refers to minimize, and the square refers to something else. So what we're specifically trying to do is look at the residuals. Like, how good does this line fit the data is going to be determined by how much error is there in the line. Hey, Brandon, you got a test on this for Wednesday. I'm excited to review. Perfect. I love it. I love it. So Brandon, is your test covering least squares regression? Are we talking about like slope, intercept, making predictions, R squared S, R squared SR? Perfect. Okay, you are in the right spot, my friend. Okay, predicted A plus BX, et cetera, et cetera. Perfect. So Lauren and Brandon, hopefully this is going to be exactly what you need. I'm glad you guys are here. I will admit, the first couple ones we did of this, it was just me talking to a screen, and so there's some good replay content for some of the old stuff, but I got you guys on this. So least squares regression has to do with residuals. So just quick yes, no. Do we know what residuals are when I mention that? Yep, how far off the actual value is from the predicted value. Exactly. And it turns out if I find the line of best fit, I'm going to end up having a sum of residuals being 0. Okay, so if you look at this line, if you look at the value of the dots above the line compared to the values of the dots below the line, it should, like roughly when you think about adding them up, it should all cancel out. So there's that one customer with the really large negative residual, and that's modified by all those customers with the small positive residuals. Okay, and so it should cancel out to be 0. And so what we're trying to minimize to like find the least squares regression line is what your calculator is doing is it's testing out a whole bunch of slopes and intercepts and plotting the points out and minimizing the square of the residuals. Okay, and that's why it's called a least squared regression line. So I'm actually going to pull up a different screen here for a second to kind of play with some stuff. So you're about to see the scatter plot on the bottom left, and then we'll talk through some stuff. And I promise this is getting to what S stands for in a couple of minutes here. Okay, and so you should see a scatter plot on your screen right now. Okay, and that scatter plot, okay, has 5 points through it. And so if I just sketch a line that looks like it's a pretty good fit, it looks like the residuals will roughly cancel out, but it's actually not the best fitting line because those squares, the literal squared residuals, I can do better. So if I'm going to just kind of reveal what the actual line is, it's that one. If I adjust the slope and adjust the intercept to match that, you should see the squares start to get a little bit smaller. And so I still have, I still have zeroed out residuals when I compare positive and negative, but now the sum of the squared residuals is much lower than it was before. So if I go back to what they had before of just a slope of 1 and an intercept, I think it was of 0. I mean, that fits pretty decently, but it's not perfect. Okay, and so the least squared regression line, boop, boop, minimizes the sum of those squared residuals. And that's why it's called least squares. Interesting. Might have been an aside for the people who are watching live. But what that leads us to is I'm going to exit out of this screen again. Okay. Okay, so that's a square residuals. Let's talk about S. Okay, S measures the standard deviation of residuals. Okay, so you just saw we want to minimize those residuals. Okay, and The residuals measure how far off the predictions typically are, or they are for each specific point. If I were to take all of those residuals and make them their own data set, where I could then like do a quantitative analysis, find like mean and deviation and all that good stuff, S would be the standard deviation of those residuals. Okay, S is the standard deviation of the residuals, and what it represents is how far are we typically off. Like standard deviation is a measure of spread, how spread out a typical individual is from the mean. In this case, the mean would be 0, would be the regression line. Okay, so if the standard deviation is 0, that would mean all the dots are on the line. Because not all the dots are on the line, there is some error going on. And S represents the typical amount of error because it's standard deviation. So typical amount of spread from the regression line. And for your tests coming up, if you're trying to interpret this, I like to treat this as a fill in the blank exercise, where you would just say, hey, using the least squared regression line to predict whatever the response variable is from whatever the explanatory variable is, we're typically off by whatever S is, whatever that number is, and then you include units. Okay, so it's similar to how you would interpret regular standard deviation. Oh, the standard deviation on this quiz was 5 points and the average was 70. Okay, Brandon's got a similar template. Perfect. So if the standard deviation is 5, you'd say, okay, well the average is 70. The average spread from 70 is about 5 points for a typical student. You'd say that for standard deviation. You're just going to say the same thing, but putting it in context with the regression line. So let's look at this specific example. In this case, S is 200.01. I don't know why it's just 200, not 200.01, but 200.01. Let's try to like type in what you would say to interpret this value of S in this context, and I'll give you some feedback on it. When using the least squared regression line to predict time in seconds from customers in line, we are typically off by about 200.01 seconds. Wait time from customer when predicting wait time from customers, the prediction is generally off by about 200.01 seconds. Okay, both of you guys nailed response variable, explanatory variable. You're saying predicting the response from the explanatory. The prediction is typically off or generally off by about that value. Lauren, make sure that you make a reference to either the linear model or the least squared regression line. So saying something like, when predicting wait time from the amount of customers using the linear model graph or using the linear equation or using the least squared regression line, the prediction is generally off. So Brandon's included that when using the least squared regression line. So Brandon, you would definitely get an E. Lauren, I think in most cases, that should be good enough for an E if you want to strengthen it and mention the regression line or mention linear model, but you've got the other components there. And so that's S, standard deviation of residuals. So amount of typically off. Yeah, we'll look at another scenario later and we'll practice measuring S from that. Okay, the other one you probably are going to get asked about is R squared. Okay, R squared is quite literally the square of R. So remember, R is a measure of the strength and direction of a linear association. Just out of curiosity, what would you guys estimate the value of R to be for this situation? So remember, it's a number between -1 and 1. Just kind of give me a ballpark. What do you think R would be in this situation? Moderates, maybe around 0.65, about 0.7. Okay. Yeah, I think you guys are both kind of in a reasonable part. That one outlier down there really does kind of throw it off. If I took that one outlier away, I would go closer to like 0.9 if the outlier wasn't there. But with that outlier there, I agree. It kind of makes it a little more moderate. It's actually, I think it's around 0.8-ish, but R squared is quite literally the square of that. Okay, and so this thing is called a coefficient of determination, but they usually just say R squared. It's going to be listed as a percent, and here's where it gets tricky. It is the amount of variation in the response variable that is explained by the regression line and the explanatory variable. So what I like to think of this is, if you were to say that R squared was 100%, okay, that would mean whatever direction your line is going in, the dots are perfectly on it. And so that every little bit of change in the Y variable can be perfectly explained by that linear equation. So every dot would be perfectly on the line. If you were at 0%, that would mean that the dots aren't even close to the line, and there's nothing you can do to help make a better prediction. There's just no association at all. So in this case, again, 100% would be a perfect fit, meaning all variation is explained by the line. And 0% would be no fit. I think it's helpful to maybe look at a specific contextual example to see, like, what the heck are we saying by this? Okay, so in this case, the template. Let me come back. Let's go to the next slide so we can look at the specific example. Okay, in this situation, R squared is 73.33. So your guesses weren't too far off. 73.33%. That is saying, if we just kind of look at the template here, that 73.33% of the actual time it takes, of the changes in time or of the variation in time, can be explained by the number of customers that are in front of you, or can be explained by the linear model that includes those two things. So just kind of like you said, when we're using customers to predict how long it's going to take, we're typically off by about 200 seconds. This is saying, hey, if all I tell you is the number of customers that are in line, 73% of the response or of the time it takes is explained just by knowing that. And so the other 27%-ish is explained by other variables that weren't included here, like how many items they had, or time of day, or how chatty they were with the checkout person. Okay, so this is explaining what percentage of the differences we see in the y coordinates are actually due to the explanatory variable. I just said a whole bunch of things in a little bit of time, and I realized I just gave like 4 different explanations. But Brandon, that's feeling pretty good. Okay, an example I do in my class, just for like another contextual example, is at the beginning of our unit, I have kids measure how long their hands are, and then we reach into a bowl and try to grab as many candies as we can. And we like plot the data and we start going through the whole unit talking about that. And by the end of the unit, when we get to R squared, I bring it back and say, all right, at the beginning, we measured the hand of a new student, make up another hand size and say, predict how many candies that person would be able to grab. And, they're usually able to get pretty close to it based on the regression model. And so when I'm talking about this, I say, okay, so all of you in class grabbed a different number of candies. Okay, whatever R squared is, that's the percentage of those differences that gets totally explained by just knowing your hand size. Some kids reach in and really kind of scoop for it. Some kids grab. Some kids just like don't really try. And so obviously it's not a perfect 100% fit. If it was, I would say, I could predict your number of candies by just knowing your hand size, and that would be all I needed. But most cases aren't 100% like that. Okay, so R squared, this is the sample response. 73.33% of the variation in wait time is explained by the least squared regression line using the number of customers in line and the wait time. Other exemplars I've seen is 77.33% of the differences in checkout time can be accounted for by the number of customers, or explained by the linear model, or whatever else. One thing to point out with R squared is you're not talking about predictions with R squared. R squared is specifically measuring the actual output values, how well they're explained by the line. So in S, you're talking about how far predictions typically are off. When you talk about slope, when you talk about intercept, you talk about making predictions and what were expected to happen. R squared actually talks about how well the line fits the actual data. And so you should not use the word prediction in your response. You should specifically mention the actual times or the specific response variable without the word prediction there. So this is not a hat situation. Coolio? Just looking for a little bit of like, yep, okay, cool. Awesome. Thanks, guys. All right, so that's S and R squared. Yep, Lauren, I interpreted that as yippee as well as yep, so you're good. Okay, let's actually go look at the computer outputs now. And so using this same example here, okay, what are the components in here that you see? So like what stuff that's on here? Good, you characters the computer output. It's like you came to the right place. Make sure you tell your friends about it. All right, so again, when you're looking at this, what kinds of things do you see mentioned in the output here? Okay, so you see R squared, and you can calculate R from R squared. Yes, you absolutely can. And so that's where I was trying to do the square root in my head. So 73, that's between 64 and 81. So that would, the R then for is somewhere between 0.8 and 0.9. So if I was actually going to get R, Lauren, if you weren't sure, I would do 0.733 and I do the square root of that to get R. So you see S, you see R squared. Okay, 147.4 equals A and 72.95 is B. When you're talking about A and B, you mean A is intercept and B is slope, or do you mean A is slope and B is intercept? I don't know if I just say the same things twice. So like 174.4, can we label that? Is that the slope or is that the intercept? A intercept and B slope. Okay. A plus BX. All right. So those numbers are both there. You got them flipped. Okay. You did. Okay. So one thing to point out, this is the way you can remember it, is notice how in the little printout they mention customers in line. They put a variable name on there. The number right next to that is the slope, okay, because it's next to the X. So customers in line is the explanatory variable. The number right next to it is going to be your slope. Okay, and the number right next to constant or intercept, constant is the y-intercept. That's a constant value. When X is 0, that's what the y is. And then the slope is what you're going up by. Okay, so that the first number listed on top next to constant, that's your intercept. And the number listed next to the explanatory variable is your slope. And the response variable is typically not going to be in here. So you'll need to make sure you read the paragraph or look at the scatter plot to figure out what that response variable is. Okay, the stuff in the top right, so that SE stands for standard error of the coefficients, the t-test statistic and p-value. For right now, in 99% of cases, if you're in the first semester of an AP Stats course, you can ignore those. You can also ignore the R squared with the little adjusted next to it. I'll be honest, I'm an AP Stats teacher and I don't even know what that stands for. I'm sure there's some kind of explanation for it, and maybe Brandon or Lauren, you got one, but I don't have it. So R squared, just use the one that says R squared. Okay. So let's look at another example of a computer output. Whew, okay, so just alone from this, without me showing you any more context here, okay, we're going to ignore those. Okay, what can you tell me about this situation? Well, you can tell me that 98.9 of the variability in the response variable is accounted for by the least squared regression line. You can tell me that. Very good. We don't even know what the response variable is yet. I would have to add on to what you say, least squared regression line relating explanatory and response, or least squared regression line using explanatory and response. Okay, which variable is labeled? Minutes is the explanatory, okay? And which of those numbers is the slope? Let's go for that. Which of those numbers is the slope? 5.215, okay. So here's the scenario. Okay, Jenny goes for walks on the treadmill. Over the course of 25 walks, she records both the number of minutes she walks and the number of calories burned in the workout. The table above shows the results of a regression analysis in a computer program. So we're going to do a few things here, but let's start with one thing that comes up when we get computer outputs quite often is, can you write the equation of the regression line defining any variables that you use? And that is thorough. Predicted number of calories burned in workout equals negative 3.822 plus 5.215 times the number of minutes she walks. And Lauren, yep. So Lauren, yours works as well. Okay, y equals 5.215x minus 3.822. You'd make sure that if you're typing this, make sure you put the hat on the y. Writing it, you put the hat on the y. So Lauren went this direction. Lauren, if you're going to do that, you'd want to make sure off to the side you label what your variables stand for. Okay. Oh, hat. The hat means that we're making predictions. So all of this computer output is coming from putting the real data into like your lists on your calculator and then spitting out a slope and intercept, but that would be the regression line. And the regression line is used to predict new values of y by inputting different values of x. And so that's the equation. Isn't going to tell you where the actual dots are. It's going to tell you where the predictions are. And then S and R squared tell you how well those dots actually fit the line. And with the 98.9% R squared, they fit pretty damn well in this case. The other way you could do it is the way that Brandon did, where you actually like write it out. And so Brandon, you saying the word predicted in your equation there is the equivalent of me putting the little hat on the calories. Putting the hat on the calories. So then we could use this equation to make predictions. So you might get asked, if she walks for 30 minutes, how many calories should she expect to burn? Okay, and in this case, it just becomes a quick little algebra problem, and you say, oh, 30 for X, whatever the number of calories that comes out of that equation, that's what we expect. If you're then told, okay, well, she walked 30 minutes and she actually burned 175 calories, that actual, they might then ask you for a residual based on that, what she actually did. So you again want to use the equation, predict the number of calories she's going to get, and then do 175 minus the prediction. And then it might, if it's positive, that means we ended up, she ended up burning more calories than we thought, so we underestimated. And if it's negative, she ended up burning fewer calories than we thought, so we overestimated. Doing some more practice of the stuff we've done earlier today. Write a sentence for S. Interpret the meaning of S in the context of this scenario. Value of S means the residuals are generally okay. Away from the line of least squares. All right, Lauren, you're close. I'm gonna go back to the template slide in just a second here. So let's see if Brandon says anything. Brandon, I'll give you about 15 more seconds, and then I'm gonna go to it. 2.3472. That's a lot of numbers in that. Generally, calories away. Okay, so Lauren, good job of using the units of calories for the response variable there. All right, we're going to go back to the template there. All right, so S, standard deviation of residuals. So we want to mention we are typically 2.347 calories away from the number of calories predicted by the least squared regression line. And so you'd want to make sure that you also mention, I think, the number of minutes. So I might clean your statement up, Lauren, to say something like this. The S value of 2.34720 means that the number of calories burned based on predictions from the number of minutes walked are typically off by about 2.34720. Something like that could be a little bit better here. If I'm not using the exact template. Oh, I would say I'm just trying to use your words here, Lauren. I would then say instead of saying typically off, I could say are generally 2.347 calories away. So you were on the right track. If I'm going to literally plug and chug into this template, I would say we're using the least square regression line to predict calories from number of minutes walk. We are typically off by about 2.372 or 3.3472 calories. All right, so we're at a point, by the way, where like I've kind of finished like the official slides part, and it's 8:40. I'm willing to stick around for about 15-ish more minutes. If you guys want to stick around and like just kind of pepper me with some more questions, and I can make up some new scenarios or go back to some old ones and use things, because I know you both wanted to review S and R squared a little bit. Brandon mentioned you could calculate R by turning R squared into a decimal and taking the square root of it would give you the way to calculate R. You both mentioned being relatively familiar with describing scatter plots like positive, negative, strong, weak, that kind of stuff. Residual calculations, I didn't do any examples of residuals here, so if you're looking for some of those. But at this point, the like official stream is kind of done. And so if you guys please put in the chat what else you want to talk about or what else you want me to address. And then we will wrap up with whatever questions we got. Go back to this scenario. So we can use this. We can use this to anchor any other practice that we do. And I can also, if you do ask questions that are relevant to some of the previous streams, I can pull up those slides as well. I can tell if the number is the slope versus the intercept. Okay, perfect. So when you're reading the outputs, I'll flip back and forth between this one and the other one. Okay, you should notice is that header that says predictor. The header says predictor is kind of giving you like that column on the left will name the intercept and the explanatory variable. Okay, so the word constant is a clue that means intercept. And then whatever the explanatory variable is, whatever number is right next to that, because it's next to the x, is your slope. Okay, so what I'll have students do is I'll make them annotate next to the bottom left, wherever they name the explanatory variable, they put an x right next to it, and then put an arrow next, like kind of draw an arrow to where that number is and write slope on it. Because the slope is always next to the x, like mx plus b, a plus bx, whatever the number that represents slope is next to the x. So find the explanatory variable on the output, the number right next to it is your slope. And then the other number in that column, or in that row, like, or column, yeah, columns go this way, is the intercept. Perfect. So of course, then you can use them to write the equation, and then you can use the equation to make predictions. Okay, and so Lauren, I remember you mentioned, you asked about the little hat there. So on this scatter plot, you've got the explanatory variables people's heights, and the y is their arm span, like, you know, how long their arms are. And so in this case, the dots represent people's actual heights and arm spans, and the equation of the line represents how long we expect their arms to be based on the different heights. So if you were to line up and like draw a little arrow from the 62 height, you see there's a person with an arm span of about 61 where that dot is, but the predicted arm span is a little bit longer than that. If you like kind of go up to the line and look over to the y-axis, it looks like it's a little bit over 62 based on a height of 62 has an arm span of maybe a little bit over 62. And so the line is for making predictions. And so if you have the equation of the line, or you have the output that can help you build the equation of the line, you can then plug different heights into that equation, or different values of x, to get predictions for the arm span. The other thing that comes up with that sometimes is we can only make predictions based on x values that we can currently see, okay, or within x values we can currently see. So in this case, the x values go from 60 to 72. I wouldn't want to use whatever equation comes out of this to predict the arm span for a child who's only 32 inches tall, because that's so far off the grid here that the regression equation might not match how the data actually goes beyond that. And that's called extrapolation. Extrapolating beyond the current data set using values of x that are way away from where the scatter plot is could be dangerous, because the pattern may not continue in the same way, so the equation wouldn't work. Okay, and so this is the different parts of the line. Okay. Lauren, how are you feeling on the different components that go into the regression line? So the explanatory, predicted values of response, and then the intercept and the slope. How do we feel about those? Doing pretty good with those. Okay, cool. Put it in the chat. Lauren, any other questions, comments you're thinking about? If we look at the whole unit, I try to think of things that I've seen students be asked before. So definitely interpret slope, interpret intercept, make predictions, interpret the meaning of S, interpret the meaning of R squared, calculate a residual, interpret a residual, look at a scatter plot and tell me the form, or tell me the type of association you see. You know, if your teacher uses old AP questions, those are pretty common in the free response. There was one year where they didn't give a scatter plot and they instead gave descriptions, and you had to explain what it would look like. So like, they said, hey, the association is strong and positive. And you had to describe what a positive association meant, where it was, as the explanatory variable goes up, the response variable also goes up. Or that linear meant when you plot the dots, it looks like a line. And you could draw a sketch to help show the answer, but you had to actually, in words, say the different components. That's come up, but for the most part, it's make predictions, interpret what the predictions mean, interpret the different components of the computer output, and use that output to help write some stuff. It's pretty typical, so stuff like this. So when this year was the question, you had to write a sentence to interpret the intercept. You had to write a sentence to interpret r squared. You had to identify if there was an outlier and explain why it was an outlier. I think those are the 3 parts of the question that year. Data point with leverage and one with influence. Leverage is an interesting term. Okay. I think leverage is referring to outliers, I believe. Influence, what that means is that the equation of the line is going to be highly affected by that point. So in this case, the customer who's the person who has only 3 people in front of them but had that really short wait time, that data point I think has both leverage and influence because it's really affecting the slope of that line. If I took that dot away, suddenly there's only a couple of points with negative residuals, and so the slope would shift up a decent amount. It also might change the intercept. And so that's really influencing what's going on. If I take away the customer who's at 5 people in line and waited about 1,000 seconds, that's not really going to meaningfully change the data there. So I realize I'm not 100% sure what your teacher means by leverage, but influential points are points that impact the equation of the line. And typically they are points that are just really far away from everything else. So whether it's an explanatory variable that's like super high off the graph, or a response variable that's way above or way below what's predicted, that influences the equation of the line. Typically, if the explanatory variable is the one with the big difference, it's not an outlier, it's just influential. And typically, if the response variable is the one that has a really big difference, that's where you have an outlier. So like that person with 3 customers in front of them, I call that an outlier. It is influencing the equation of the line, but what I'm going to do is pull up a different slide for this, Lauren. All right, Lauren, so you should see on your screen right now 4 different scatter plots with, in fact, the exact same regression line for all 4 of them. All right, I want you to look at the bottom right. At the bottom right, if I take that dot away from the top right corner, that is going to severely change what the regression line is. I refer to that as an influential point because it's really going to change what's going on here. Bottom left, there's that big outlier, like way above the others. That's also like an influential point, but I think that seems to be more like leverage. Okay, now that I'm talking myself through this, I realize I'm not 100% sure if I can answer your question all the way, but bottom left is an example of a point that is really far away on the x-axis. And so that means like the line of best fit now really has to go to that point to like minimize the squares of the residuals. And so that's a really influential point. But the association there is not positive. Like it's not a strong positive relationship. In fact, if I take that dot away, there's no association at all because it's a vertical line. Bottom left, there is a pretty strong positive association, but there's that single outlier with a really large residual that influences the equation of the line, but doesn't change the fact that there's a positive association. So maybe the leverage idea is like a point that changes the type of association that you have. That could be what they're referring to. And so I apologize that I'm not totally all the way 100% in on that. But at this point, Lauren, did that help address your question? Hopefully a little bit, maybe a lot, or maybe not at all. Super helpful. Okay, cool. Yeah, and so this slide is a really good example of why describing the association is important. Everything that we do with slope, intercept, residuals, all that stuff is referring to linear models. Okay, and the ones on the left clearly are fairly linear associations, and the ones on the right are not. but they all have the same value of R. They all have the same least squared regression line, okay? But they're not all as well described by that regression line. The ones on the left, I think, are pretty well described by it. The ones on the right, top right is a super strong nonlinear association, and the one on the bottom right just has that single really influential point that really changes everything, and kind of messes it up. All right, so we're closing in on an hour. Thank you guys so much for attending. We've talked about slope, intercept, R squared, S, influential points, describing association, what a residual is, what the little hat stands for. Just before we go, remember you guys can follow everything that we do, okay, at Fiveable, so you get updates about what stats things are. If you have a Fiveable account, okay, you can watch replays of our previous materials, okay, and so that includes both parts 1 and 2 of this. This was kind of the part 3, and then as we go through I know we've done some other stuff about univariate data, and like we call it CUS in my class, or some people call it SOX, talking about center, shape, spread, all that stuff. So you can check out some replays, and then just stay tuned for updates, and be sure that if we ever send out surveys, okay, and I know there can be bias involved in surveys, talk about that in my class too, but if we do send out surveys, please tell us what kinds of things you want us to go over, so that we can tailor this to your needs and make sure that we hit your stuff. So hopefully this was a good test review, and if there's no other questions, I will say good night. Thank you guys so much for coming, and I hope to see you on a future stream.